I got the flag to say I can begin. Thank you very much for coming. I appreciate it. It is 5 p.m. on the Wednesday evening, and we stand between you and the party. So I appreciate your coming, and I hope that we'll reward that with a deep dive on some of the performance aspects of Windows on ARM. My name is Marcus Perryman. I'm a principal engineer in the Windows team, and I have two other speakers with me who will introduce themselves at the right time when they come up. Windows on ARM has been around for quite a while, about 8 years I think it is, with the Cobalt PCs launching in 2018. But with the launch of the Snapdragon X Elite range of system on chips 12 months ago, powering our first Qualcomm Plus PCs, they began releasing from all of the major manufacturers in the industry. Now that ARM system on chip is perfectly aligned with the goals of Copilot Plus PCs. The first being to bring a major step forward in mobility for Windows users. And it does that by having a power-efficient CPU that runs a silent device, nice and coolly, that sits on your lap. Now, because of that, the second pillar is to give device manufacturers bigger freedom to create new IDs. Less battery, less cooling hardware means they can innovate, and they have in the devices that we've seen. And the third thing, which is probably the most important, is bringing AI inferencing experiences right there under your fingertips on Windows PCs. And that's done through the neural processing unit that the Snapdragon X Elite puts on that chip. And we've seen some great devices that have been released from Asus, Surface, Dell, Lenovo, HP, et cetera, that are in market today. But that's powered by a very interesting piece of silicon that is slightly different than the experience you've had with Intel. It's got a stack of cores on the top range, 12 cores in 3 banks of 4, one of which in the Snapdragon X Elite is an efficiency core, and I'll touch on that a little bit later. It's got the capability of 64 gigs of RAM, and it's all backed with a 45 TOPS NPU that sits in that chip. Now, this session is about how do we, as software developers, get the best out of that chip. And how do we do that in a way that drives battery consumption down and efficiency up? So there are 4 key pillars we're going to talk about in this session. The first is about getting as close to native as you can. The second is about staying on things that have already been done, so don't reinvent. The third is about staying up to date on tools and libraries. And the last is the narrowest of all. When you do need to optimize, when the compiler is not doing enough, how do you go and do that on ARM silicon? So let's start with the first and a quick demo. So here I've got my application, my demo application, that's been built in C++ to highlight some of the aspects of the performance. Right now, it's an x64 app, and I've literally just cloned it down onto my machine. So the first step is to go and run that. So I've selected release x64 as my profile, and I hit go on an ARM machine to see what that looks like, what the performance is like on that machine. And there's my app. Now you'll see, if I zoom in here, it does tell us it's a release build. It's built by MSVC. It's targeting x64. When it looks at the CPU, it's seeing AMD 64. So what we're seeing here is our emulation. The Prism emulator is kicking in. But underneath that, it identifies that it's an ARM 64 machine. OK, so let's go and run this. Now, I've chosen the particular library to highlight certain aspects. It's not, it's not general purpose code. It's actually doing a whole bunch of tight maths. And we see it takes around 4.6 seconds to render this Mandelbrot image, which is a Mandelbrot rotated in 360. I'm sure you've all seen it. OK, that's great, 4.6 seconds. Now let's see what we can do by converting that to ARM native. Well, how do we do it? Well, the first step is we need to go into our configuration manager. So here we can see it's x64, and I'm building for x64. I'm going to select New and Change Platform to ARM64. There you go, ARM64 selected. Click OK, click Close, and debug. So 4.6 was it? I think it was for the x64. Let's see what we get after we've built that. Now, for most applications at this point, you are done with the conversion. So again, let's just quickly look at what we've got. It's a release build, MSVC, ARM64 on ARM64 for an underlying ARM64 machine. Great, so we're right through top to bottom, ready for ARM64. Let's give it a go. 1.5 seconds. Okay, so we've got that. Now, bear in mind, I've chosen that very specifically. Mileage on the difference between Prism emulation and native varies really significantly. The Prism emulator is hugely optimized, and you'll see it in several other demos where the Prism emulator and the ARM native are very close. But there is always a gap, and it's always closer to native that you go, the better performance you have. Okay, so that is MSVC. Now, we're not limited building for ARM with just the Microsoft compiler. So if I wanted to, we're fully supporting. So I go into the properties, drop down, and select Clang. I can switch my compiler over to the Clang CL. Now, I'm actually using Clang CL 20. So I've redirected the default, and I've chosen the latest version of Clang here, just because I can. And now I can hit Go and build that again for ARM64. Now, why am I doing that? Well, with ARM, what we're finding is that the compilers are actually at different stages of optimization. Now, I would, a top tip, as this is a tip session, the top tip here is make sure you test your code on both or all of the compilers to see which one does the best. Now, you'll see here in my specific example, it's about 5% slower on Clang for my specific code than actually for MSVC. So that should just show you it's Clang, so you can see it's actually built here. Same thing, Clang. So it tests, that's the key thing. Now, last thing I want to talk about, I told you there are 3 banks of 4 cores within the device. Let's pull those up. Now, a lot of questions I get from folks that are porting applications is, well, do I need to care that there are efficiency cores on the device? Well, 4 of these cores, and I happen to know it's the top 4, are efficiency. The rest are classed as performance cores. Now, if I ramp this up maybe to 1,000 by 1,000, so it takes a little longer, we'll test that out. And I can set the affinity to a high-powered core now and get it to render. Now, it takes a bit longer, but you can see the last core, I've picked that specifically, just because I know that's a performance core. I've picked that specifically to see how fast we can run it on the performance core. Oh, what was that? Did anybody see the number before I accidentally clicked? It was 10 seconds. 10.4. All right, we better wait for it to finish, otherwise it will get very upset. 10.4 is pretty consistent. Now, if I select low, I've picked another core, which is the efficiency core. And I know that the first core is that. Let's see what the difference is. So 10.4 versus 12. It's usually about 10% difference. Now, the only difference between these 2 cores is clock speed. So do you need to care? Well, no. The scheduler in Windows will do a great job of putting your app on the right core. There are some very narrow scenarios where you might, if you're running on less than all the cores and you're maybe running in the background, then maybe you want to do that in a test environment situation. But for live applications, you don't need to be concerned about the core performance. So a word about ARM64 EC. So ARM64 EC is a brand new ABI that we've brought to ARM development, and it's considered a native binary. So ARM64 and ARM64 emulation compatible, or EC, both are native technologies on ARM. When would you choose one over the other? Well, the purpose of the emulation compatible is to help you in 2 key scenarios. If you have a very large app with lots of libraries, and it's going to take you multiple years to get there, or a long time, multiple weeks maybe, you can choose to switch to ARM64 EC without compiling all of the libraries. You can mix x64 binary code and ARM64 EC code in the same binary, overall executable, and get native performance for the application and for the code that's ARM64 bytecode. The emulator will only come in for the code that requires the emulator in order to pick up and translate those bytecodes. So I said one is a large code, the second large code base. The second place where this is incredibly useful is for a plugin system, where maybe you've got legacy code that you don't control. Now, in that situation, it's worth considering, but it is not the first place. The first place is ARM Classic, the main ABI. If you can get there, go there. If you can't, EC is something that's worth considering. Let me show you a quick demo of mixing the code together. So we'll switch over to, and this is a top tip here, by the way, if you're doing presentations, never number your demos, because somebody's going to shuffle them around, and we'll end up with demo 3 being demo 2, but you know, that's a by the by. So here I've got another application. It's doing something slightly different, but over on the right-hand side in my project, you'll see I've got 2 libraries. At the top, we've got ARM64 Neon, and underneath, we've got an AVX2 DLL, and then the last one is an AVX lib. Now, let me quickly explain. Neon is the SIMD registers, and I'll talk about those in a second, inside of an ARM chip. AVX2 is an extension that Intel put about 10 years ago on their silicon, and AVX is even older than that. So I've got 2 libraries. One's a DLL linkage, one's a lib linkage, and then the ARM Neon is a lib linkage as well. And I'm going to show you that I can build all of those together into a single app. We'll test the, actually, I'll tell you what, let's switch straight over and see that running. So here's my app. I'm building currently x64 for 3 of those, and ARM64 for the ARM Neon. They're actually linking together. That actually does link. And the reason it links is because I've actually cut out all of the Neon references while I build that. It's just a simple trick to get that going. But what I'm going to do is switch this over to ARM64 EC, where you can see I'm now building demo 3 as ARM64 EC, and I can link in my ARM code. Right, let's give that a go and see what that comes out like. So if I build that, just thinking about it, build nil3. But it's failed. It failed to build. In fact, it built successfully. It's failed to link. And if you look, all of those Neon references have failed. Why? Because you can mix ARM64 EC and x64. You cannot mix ARM64 EC and ARM Classic. They must be built as EC in order to match. So I need to go back in to my configuration and switch that one over to EC. And now I can build it because it will link those things together. So we'll just give that a run, make sure it works. That time the link works and the code executes. Now the other thing I was going to highlight here is for those of you that know where we are with Windows today, that I have been able to run AVX and AVX2 code on this device. Let me just zoom that in so you can see. So you can see I've got a float scaler in x64 at the top, a float scaler in ARM64, which is ever so slightly faster. Remember I told you that the Prism emulator is very good. You can see that here. You can see I tested for AVX, and it's there on this system. I ran the AVX. It's actually slightly quicker because the Prism emulator is great. I ran it using our Neon extensions, and it goes significantly faster. And then we've got the integer AVX2 stuff underneath. OK, let's switch back. So I mentioned about we'd look at a little bit more detail about the AVX stuff. So let's start here. One of the things that's quite important to understand is the differences between Intel and ARM. Now, an ARM chip has 31 general purpose 64-bit registers. The 32nd one is used for flags. Now that's the general purpose stuff. That's what the compiler's going to put code on. That's where it's all going to execute. It's also got 32 128-bit SIMD, or simultaneous instruction multiple data registers that you can chunk up into different sections. They're addressable as V, as D, as S, and so on, at different sizes. So I can do multiple operations together. And those are the ways that we speed up. They're similar in their technique to SSE silicon on Intel, AVX silicon, and AVX2 instructions as well. Now, the reason I'm bringing this to your attention is because when you think about ARM64 EC, the application binary interface, the ABI, restricts the code you run around the Neon registers to just 16. We need the top 16 to store the state. Now, with AVX emulation coming, and I'll tell you where, actually I'll put it up here. So it's 24H2 is when we've enabled that. At the moment, it's an enable list. So only the apps that we tag will get that emulation. Whereas in Canary, it's for every app. Now, in those situations, when AVX is enabled for your process, we use an extended state store, which unblocks those top 16 registers. Why does that matter? Well, it matters because when you're trying to run code in that middle ground in the ARM64 EC, you can now, when AVX emulation is available, get the full power of the Neon registers. An example, FFmpeg have done the work in that EC space, and they're bringing their performance now for EC FFmpeg up to almost equivalent of the ARM Classic implementation. One thing I must say, you must test. So AVX emulation is tagged to a process. You must look for it before you use it, because if you break the ABI, your app will crash. And so you need to know that it's there. Okay, takeaways. Number one, port to native. Get as close to native as you can. And number two, think about ARM64 EC as a way to do that. Look at it for complex apps and for plugins. And remember, it is a native ABI, but you cannot mix ARM64 Classic ABI with ARM64 EC. Okay, let's move on and look at our second pillar, which is don't reinvent. And for that, I'm going to invite Chris to come and take us through. Chris.
Thank you, Marcus. So I'm Chris Goodger, and I work for ARM, and one of my roles is looking after software, especially around performance. And one of the great things I found this week here at Build is talking to lots of people on all the other stands on the exhibition and the people who've come and talked to us on the ARM stand, is how many people have already done this porting journey that we're talking about, that they've managed to do it relatively straightforwardly, like you've seen, hopefully just clicking one or two buttons, and they've got their code working on their ARM systems. The important thing now is how do we go from there to getting more performance? And the story is not very different from any other platform that you develop on. One of those first rules to think about, though, is how do you make sure, as a developer, that you can very quickly take advantage of all the work that goes on around ecosystems. So ARM definitely thinks about Windows as a first-class ecosystem, where we've got lots and lots of developers all the time, and with the advent of new ARM devices coming across multiple different markets as well, we're making sure that we're pushing each of these ecosystems to work with the libraries and the tools there to increase performance. So the thing about libraries is you can just pick up that bit of work and put that into your application. Somebody else has specialized in working on a very particular problem. They have built this into a library. Other people from the ecosystem, people like ARM, people like our partners, have all collaborated along with it to bring some of these libraries to mean that you can just link it into your application without having to try and reinvent the solution yourself. And you'll see later on when we talk about hot sections of code that there's a lot of work sometimes in being able to take a full advantage of the silicon that's underneath you. You, as a developer, want to concentrate on what it is that you're doing best, what separates your application from anybody else's. As we think forward then, what do you want to do? You want to make sure that not only can you pick up this code, that you can run it today, you also need to make sure that it keeps working as you go forward. And GitHub Actions are being now available not just for ARM, but for Windows on ARM. So open source projects can get to take advantage of this. They can make sure that anybody checking code in doesn't break the ARM builds and doesn't break anybody else's builds, all in the same way. So this is a really important step to be able to take for actually application developers. In terms of Windows and what's been optimized for ARM, then there is such a long list of things that are there. We've picked out a few here. There's more if you go and click onto that Linaro page at the bottom, but even that will not be a comprehensive list of what is available. So I thought I'd pick out a couple of these just to actually talk about why they're important to the users like you. So the VFX platform, this is something for the VFX community. They've gone ahead and they've defined a set of libraries and tools that people in their industry want to be able to use, but they've said, these are the versions that we've tested together. We've made sure that they all work, and that they all work on ARM as well. So this is a nice thing you can go and reference to see these things that are already porting and working together and verified to be giving the truth. As part of that, some of those things in there include maths libraries. One of the things that we've built as ARM is ARM performance libraries. Now, that's the kind of equivalent of 1MKL, which exists on x86, and you can find in that VFX platform. On ARM, you don't want to be running that x86 binary. You want to pick up something that's been properly optimized for ARM to include linear algebra, fast Fourier transforms, sparse, and random number generators. So ARM Performance Library, great one to be picking up for that point of view. And I'm also going to point out there SSE to Neon and SIMDE, which Marcus will come back to in a little bit. But one of the hot topics we've had this week around build has obviously been around large language models and machine learning. This is something which is very important to ARM across all of our ecosystems. So we have people running on big cloud machines, on laptops, on mobile phones, on edge devices, and they're all trying to do AI these days. We're kind of at the center of all of this work going across the globe. And what this means is there's a lot of different hardware out there trying to solve essentially the same problem. At the heart of it, there's these convolutions, these matrix multiplications that need to be done. So we've built a library called Kleidi AI, which we've worked really hard to embed into lots of the big frameworks. So Onyx Runtime, TensorFlow, PyTorch, they've all got this now embedded into it. There's, I'm told, literally billions of deployments of this across the planet now. So what does it actually do, though? By having it there, it automatically manages to recognize the sort of device you're running on and provide acceleration. You can see some of the numbers on the right there for Onyx Runtime, but this is just one example. So you as a developer, if this is what you're doing, you can pick that up. But more than this, you can actually go online onto GitHub, onto our GitLab here, and look at how we've done these implementations to see which ones it is you might want to pick up for your cases. So as we think about it there, we've got libraries that we want to stay up to date with, but there's also compilers and runtime tools, which are also important as well. ARM contributes to both of these, both GCC, LLVM, and we work with the Microsoft MSVC team to make sure all the right advantages are going into there. We work with the .NET team. We work with JDK teams as well to try and make sure that they're all coming along for the journey. And so I'd like to introduce Jamshed to give us a lovely demo of this.
Thank you. Hi, I'm Jamshed. I work on our first-party developer tools and runtimes for Windows and ARM. Microsoft keeps the Windows OS, our compilers, and our runtimes up to date with the latest innovations in ARM and available hardware. So to benefit from these innovations, you want to stay on the latest compilers and runtimes. The demos you saw so far are all C++, but if you're a .NET developer, this one is for you. I'm going to show you how .NET uses Advanced SIMD. Advanced SIMD is an extension of the ARM architecture for vector processing capabilities. It allows for efficient parallel processing for applications like image processing, machine learning, and cryptography. Advanced SIMD is accessible via intrinsics and uses multi-register load and store intrinsics to reduce memory access overhead and improve data throughput. Let's take a look. Yeah. This is the source for the base64 encoder and decoder API in the .NET runtime. Here you can see we first have a test for whether advanced SIMD instructions are available. If it is available, it's going to call the try-load ARM vector 128x4 method. Let's see what this can do in action. So I have a UTF-8 encoded blob here, and we're going to decode it using the simple app. First, we're going to do this with .NET 8. I'm using a fairly large file, otherwise this operation would be over in milliseconds. And we will now do the same thing with .NET 9. The write side is obviously faster by about 20%. Now, why did I take the base64 decoder as an example? It's because many protocols transmit text in UTF-8 encoding. Apps do things like sending binary objects over streams, decoded on the other end. There are JSONs with blobs embedded in them. So I took this as an example, but we have done many such improvements throughout .NET. Now, if you're a Java developer, then this one is for you. At the start of the session, Marcus showed a demo with processor affinity. And that can help you scale out your application sometimes. But how far can we push that? This is an Azure Cobalt 100 VM with 96 cores. I'm going to use the spec JBB 2015 benchmark as a workload to test the runtime. And you will see I'm using JDK 2103 here. The benchmark takes about 10 seconds to warm up. There's a warm-up phase after which it's going to go and do the real measurement, so we get some stable numbers. So give it a second. So what's going on here? I have 96 cores, but I'm seeing only about 2/3 or 64 cores are engaged out of 96. What's happening is Windows processor groups can have a maximum of 64 logical cores per group. OpenJDK uses the getSystemInfo API to get the number of processors on the system, and that API is returning the number of processors in the current group instead of all processors across all groups. So even though we have more than 64 cores, we are only seeing 64. So we made a change to make all cores across all processor groups available to the app. Now this only works, what I'm about to do only works on Windows 11 or Server 22 or later, because it depends on a change in the OS. And this time around, you will notice I'm using JDK 2107. And that's the only change I made. And when you look at this again in Task Manager, you see all 96 cores are being used. I made no changes to the source for the application, for the benchmark. All I did was change the OS and change the runtime to use the latest fixes we have. So what are our takeaways today? We want to always stay on the latest version of the compilers and runtimes. And often, that's all you need to do to take advantages of the latest changes and innovations that we have in ARM. We have a whole ton of performance improvements in the .NET runtime, in the .NET 9 runtime. Take a look at that blog post or the QR code, and you'll see them. Chris?
Thank you. Thank you. So We come to our fourth section now, the optimizing hot code. Now, this is not going to be something that everybody does. Hopefully, you can pick up the libraries to be able to do the things you want. The compiler can do the magic that compilers do to make your code run well. But sometimes you can find out that you really need to get slightly deeper into the code that exists that you've got to try and be able to get more performance out of it. So the first step of this is to profile. Whatever the tool is that you want to use to do your profiling, whether that's Visual Studio, whether you're doing that using WPerf, or something else entirely, make sure you work out the right things that need to be looked at. Only then do you start to look at changing the code in this section. Now, you probably have got experience, if you're interested in this section, in how to go about doing these things, whether that's adding new compiler switches, whether that's rewriting things during doing intrinsics and things like that. Not going to go too deeply into those things today, but what we're going to talk a little bit about is making sure that for ARM, you know what there is available for you. So as an architecture, what ARM does is it keeps developing it. We didn't invent Neon 12 years ago or whenever it was and stop working on it then. We keep doing updates to the architecture all the time. Some of those, they're about security, to make your system safer for you and your applications. Sometimes they're around performance, to make sure that the right sorts of advantage can be taken by software for, as software develops, as people learn more about what could really accelerate the sorts of workloads being done. So, for example, when ARMv8 was invented, machine learning was not something like it is today. Adding things like floating point 16-bit instructions, that was something that was added a while back, and these added instructions keep coming along. So matrix multiplication and dot product instructions, they're available today, and you might not think about them as things that go on particularly often in your code, but we'll see in a second an example where they are actually used. And there's big features that come along as well. So SME is our matrix computation work that's coming online at the minute. And that is definitely ideal for machine learning. So here's an example. So it's from a video codec. So this is what's used to encode or to decode things you run on your laptop before you send it to the cloud to store in some big video database, to stream to another device, or downloading your video from whatever your video provider is to watch on your device. There's lots of encoding and decoding of video going on all the time. And what we have to do is, as ARM, we make sure we're thinking about how can we do this as efficiently as possible on the devices that people are using. So to start with, there exists for x265 here a load of C code which does this encoding and decoding, and the compiler does all its magic. And at that point, we've normalized the baseline to 1 there across each of these different speeds of doing the encoding, from very slow encoding to give high quality compression to ultra fast encoding, which will not be as good from that point of view. But the next blue bar going up, that is when we add rewriting these loops which exist in basic C code to use intrinsics. So this is understanding how we use ARM v8.0 here to rewrite using Neon code to make it go faster by doing as much SIMD operation as possible. And you can see here we've increased performance by over 100% across the board. So that's a pretty significant increase. And if we then go to the next step of actually looking what hardware features have been added in later years to this device, you can kind of see that across these cases, we're adding 20–25% more performance again on top of this. And that's through things like the dot product instruction. So if you are the sort of person that is going to be able to write intrinsics code for the sort of application you're doing, make sure that you have a look at thinking about what of the added instructions that have gone into the architecture that you can use. Make sure when you write your code, though, that you've put guards around it, like you've seen from some of these other examples, in terms of checking, have I got this feature enabled? Because you want your application to work everywhere. The idea that you're checking that it works for 8.0 to start with means it works on every ARM device. A small set will have these dot product instructions today. 5 years' time, everybody probably will be having these. So that's a good example. If you want to see examples of what this code looks like, feel free to search on the web for ARM developer video codec optimization. Lots of explanation there with lots of code you can pick up and show. OK, thank you. And Marcus? I think you're up next.
So that's been quite interesting to see how ARM do it. Let's see if we can bring that back to the Copilot Plus PCs and see how you can actually go and do that on Windows today. So my last demo, just to get this thing signed in. And we'll switch over to this guy. There we go. So on my last demo, I want to actually step in and take a look at some of those SIMD optimizations and how you can start to use them. So here I've got my demo 2. Remember, I said don't number your demos. Let's give that a run. Oh, that's the wrong one. Let's try this one here. There we go. So here I've got the application again. I'll give that a go, and we'll see what we're actually running. So I am running this under emulation just to give us a baseline. So it's a release build, MSVC, and x64. So it's running under the Prism emulator. And what this code does, I've gone back to Mandelbrot because I actually found a great library which has got all 3 implementations. I thought I'll borrow that. And so it's got Neon, it's got SSE, it's got Scala. Actually, it has AVX as well, and you'll see that code. But when we run that under the emulator, under the Prism emulator with SSE, we get about 1.2 seconds. Now, of course, like we said at the very beginning, we should always switch to as close to native as possible. So let's go and select Release, ARM64, and go ahead and build this Mandelbrot to pull in. And if you look over here, you'll see I've got each of those implementations, including a Neon one, which it will now pull in and use the intrinsic for that. So let's put that up on the screen next to the other one. There's my reference, 1.2 seconds. As you can see, it is now MSVC ARM64. So, of course, it's going to go faster, right? Let's see what happens. Oh, wait. That's not working out, is it? Why is that going slower? That's like 4.5 seconds versus 1.2. And yet, I'm definitely native. Now, for the sharp eyes, you've probably got a clue here. But that's not the right way to do optimization, is it? We've been told, profile it, and then you know what you're doing. So let's go ahead and actually profile this to find out what's going on. Well, normally you would run a profiler in release mode, in the mode that you're actually testing. But for demos, it's a lot easier if I bring the symbols in and we don't have to go through the bytecode and work it out. So I'm just going to demo this under debug. So I've switched to that. And then here I've got the performance profiler under Visual Studio available for me on ARM to go ahead and run that. Now there are, lost it again, let's go. While that's running, and here I get to select what I'm going to profile. Visual Studio gives me an option of CPU, memory, and various other things. Just for this one, we'll go ahead and select CPU. Now that'll start the app, start grabbing the profile information, and start recording it so we can actually see what's going on. Right, there it is, hit draw. We don't need to leave this for very long. You can see the CPU is running. Okay, it looks pretty small, but actually remember it's single-threaded. So 12 cores, that's about 100% of one of the cores. That's long enough. We'll stop that. There are 3 profilers that you can use. So the first one I'm showing you today is Visual Studio Profiler. It's very convenient. It's capable, although there are more capable ones if you need to go deeper. There's the Windows Performance Analyzer, which will allow you to look at a lot more detail of what's going on. And there is also Windows Perf, an open source, or WPerf, an open source profiler you can go and grab, which can actually make use of the internal dedicated performance counter registers to help you get things figured out. So here I can see there's a whole lot of, I think it's green. Let's go with green. Now, if I select a section here, the Visual Studio Profiler will help me by saying where the time's being spent. And here, when I look at my call stack, it's saying actually 96.54% CPU is in Mandel Basic. Now, I think that might be a candidate to take a look. So I look in that, Visual Studio will now annotate for me where that time is spent in each of those lines. And I can see that 60% of my time is in this float operation. But wait, this is supposed to be Neon. Why is it running C code? Ah, there's the trick. I need to go figure out why it's not calling my optimized code path. Coming back to my code, I've got this guard around my Mandel Neon implementation. And this is a common problem. So top tip, when you're doing conversions to ARM native, make sure that the optimized code paths that are already existing for the silicon-specific stuff are being enabled for the Windows code path. So we'll do underscore M 64. There we go. So now I can include that in my ARM build, and we should see the Neon code path being executed when I run that. Yep, okay, we're good. We've got Neon. You know what I didn't do? Let me stop that. I didn't switch that back to release. And then we'll hit F5 again. So we saw the Neon code path being used. We didn't see the advantage of the optimized code. So let's give that a run. And we're at 1.2. And you know, the algorithm isn't mine. It's about a 10% difference between them. It's enough to demonstrate we're using the code path. But what happens if I haven't got a Neon code path available? Well, you're still not done. You can still use the optimized code paths that might exist for Intel already. So just down here, I've got an AVX and an SSE, and there's the scaler, the basic below that. I want to use the SSE one, so I'm going to hard code is SSE2 supported, which is down here, and I'm going to tell it that, you know what, we're actually going to use that and pretend we're on that code base. I'm going to come across to my SSE2 implementation in here, which is guarded by x86, x64, and I'm going to tell it to include that. Now that, once let's try that. That's better. You can see that all the types it's saying it doesn't recognize. You'd expect that. But there's this project that Chris mentioned called SSE to Neon, which is pretty cool. It's a header file only project which will translate those intrinsics at compile time from SSE2 into Neon equivalents. Now, if you're looking for the last 0.01% of optimization, you probably still need to hand optimize. But this is a great way to take something that's performant on x86 very quickly onto your ARM device. So let's just kill that one. And we'll just run this and see how that works. There we go. So when I run that, and we now see the SSE2 coming back in here. So it's running the SSE2 code path, and our performance is, again, slightly faster than the SSE through the Prism emulator. Although, as I said, Prism emulator is pretty good for this sort of thing. And I think there's one last thing. OK, so the one last thing I wanted, Jamshed's going to come and tell us about is profile-guided optimization. Jamshed.
Thank you. So we are almost there. This is our last demo for today. Profile-guided optimization, or POGO, is one of my favorite C++ toolset features. POGO is used to optimize application performance by leveraging runtime profiling data collected from running the real app, so the compiler can make informed decisions about optimizing the code based on actual usage patterns. So how much improvement can POGO have on the performance of your app? Let's take a look. Here I have a sample app. It's Conway's Game of Life. It's a simple demo of evolution. Cells are born, stay alive, or die based on neighboring cells. Now, the reason I picked this example is it has a bunch of nested loops it computes the state of each cell, the evolution of each cell in a loop. As we can see, it's doing about 100K calculations per second. Let me show you how simple it is to use Pogo to optimize this application. To use Pogo, we add a couple of compiler and linker switches. I've already added the /GL, or whole program optimization switch, and /LTCG, which is link time code gen. And now I'm going to introduce the /gen profile switch. /gen profile creates an instrumented executable and a profile guided database PGD file. When the instrumented executable is run, profile data is going to be captured. So let's build this app. So we're going to run the app. As we run it, the app is instrumented, so it's gathering real usage data and storing it. I'm going to exit the app. We'll take a quick look, and we see the profile data has been captured. So the next step is now using this profile data. How do I do that? I go back and change the linker switches again. This time, instead of /gen profile, I'm going to use /use profile. And we will build again. As you can see, the linker is spitting out a bunch of things here. It's telling me how many functions were optimized using the profile data, which ones are inlined and which ones were not. Let's take a look at that. Give it a minute to stabilize. And we can see here it's doing about 120,000 calculations per second this time around. So that's about a 20% improvement with no change to the app. All I did was run Pogo. Thank you.
OK, let's wrap it up. So takeaways from that section, we've showed you how to use a profiler. And I'll reiterate again, I think it's the third time we said it. It's important. Don't guess. Use the profiler. Go find out where your code needs it. If it does need it, get in there and use the silicon-specific operations like C intrinsic operations. Or if you need to, go down to assembler. We have ARM Assembler 64 available in Visual Studio to go and actually handwrite your own assembler as well. Use intrinsics and assembler. Use SSE to Neon. And I forgot to mention, SimDE is a second header file only project, open source project, that actually also supports SSE, but it also supports AVX operations as well. So if you're using AVX on Intel, use one of those two to get you started. And don't forget the compiler. So the compiler, as I said at the beginning, Clang, MSVC, produce different profiles for code. Make sure you use them, test them, find out which one's right for your code. But use the options that are there, like PGO, like other O2, O3 options to see what your code is doing. ARM for Windows is pretty mature, but there are still things that we're learning and improving on. And those are key things to play with to make sure you're getting the best performance. So there's the 4 pillars. We've been through the 4. Run as natively as you can. Don't reinvent. Use the libraries that are there and already optimized. Stay up to date. Take advantage of the work that we're doing, that the open source community doing, that the frameworks are doing. And when you need to, when that, come down that funnel to the very narrow end of it, and you have to roll your sleeves up and get in, then go and optimize it with the right opcodes, with the stuff that's relevant after you've profiled it and after you've used it. If you want to learn more about this, we'll be on the booth, not tonight because that's the party, but tomorrow morning, bright and early. We'll all be there ready to answer your questions on that. We have Qualcomm, we have ARM, we have Microsoft, all there to answer your questions. But I hope you'll see that ARM and Microsoft are a great pair, and we're working really hard to bring the best performance we can to your applications. Why? Because our customers on Windows need that. And that's what's going to deliver the Copilot+ PC promise of mobility, all-day battery life, and that AI experience at the edge, which is really important. Thank you very much for listening. If you've got questions, we have a few minutes, and come to the stand and to the mic, and we'll take them. Thank you. Who's got the first one? No pressure. Great. Everything answered? We could always chat at the party. You know, let's 10 minutes towards the party. Let's go. Thank you very much.